My name is Elena Kalinina, and I am a technical project manager in Yandex, and I am working in YDB team. YDB is a data platform which allows you to work with OLTP processing, OLAP processing, and persistent queues within one system. And I'm going to tell you how we created a system where you can operate tables and persistent queues within one transaction. So first of all, I will talk about main YDB architectural principles, and then I demonstrate an approach how to unite tables and persistent queues in one system, and third, we deep dive into our transactions which combine tables and persistent queues. We call them topics in ACID way. First of all, several words about YDB. YDB initially was a distributed data management database system, and first and the main part of YDB is transactional processing, which has distributed storage and can operate petabytes of data with millions of transactions per second. And our internal installation has thousands of nodes. Second part of YDB is YDB topics. It's our implementation of persistent queues. The nearest analog is Apache Kafka. So you can deliver data, stream your data between applications, and we provide exactly once and at least once guarantees, and we can provide high loads of gigabytes per second of writing speed. Third part is analytical processing OLAP, which can be used within one system with first two parts, and we can provide analytical reports with our data. This analytical processing is not a topic of my today's presentation, but you can read about it in our public materials. YDB is published under Apache 2.0 license, which means you can use it. This is the most permissive license. You can use it for free for commercial purposes. So we have row-oriented tables for OLTP, column-oriented tables for OLAP, and YDB topics for persistent queues. YDB has fault-tolerant configuration, which means it survives disk, node, rack, or even data center outages. And YDB can automatically recover after disaster with minimum latency disruption for users. Also, we have independent horizontal scalability of storage and computational nodes, which mean you can add nodes at runtime if necessary. And you can operate with your data and scheme with our rich SQL dialect YQL, and we have ACID transactions. Of course, YDB has had transactions with tables before, and recently we added a possibility to have topics within the same transactions with tables. And this is the main topic of my today's talk. So several words about topic. What's this? Main features. First of all, YDB topics is a realization of persistent queues with YDB. As I said, the nearest analog is Apache Kafka topics. If you worked with it, you know it. So the main features is reliability, which means no losses of data, and possibility to work with big amounts of data. Our internal installation has overall write speed up to 200 gigabytes per second. How can you work with YDB topics? First of all, we have our own YDB topic API, and we provide SDK for this API in many languages. And this YDB topic API supports all YDB topics feature. For example, exactly once delivery, our main topic today, transactions with tables and topic, and others. And recently we supported Apache Kafka API because Kafka is a common choice for persistent queues. And if you want, now you can use YDB topics everywhere where before you used Kafka topics. And you can use YDB topics with standard Kafka instruments or some outer software. As YDB topics based on YDB platform, it allows us to do close integrations. For example, we have change data capture when you capture changes from some table and stream it into the topic to some outer consumers. And we have now transactions with topics and tables. When do we need transactions with tables and topics? Everywhere and every time when we need atomicity and consistency of our changes in tables and topics. I have here 2 examples, but we can generate much more. So first example, for example, we need to enrich information about an event from with the table data. So we read simple event from the topic 1, then we read some reference data from the table, process event with this, enrich event with this data, and write rich event info into the topic 2. So we need to do it all in one transaction, so atomicity and consistently, to have not to lose any data and not to duplicate any data. So, and we can provide it by some user code, or we can provide it by transactions within the system when we begin transaction in the before the first action and commit transaction at the end. Another example, more technical, resharding task. Let's input topic has all events, and we want to distribute these events between partitions of output topic by some rule. So we read an event from input topic, define output topic partition by event data, and write an event to the appropriated output topic partitions. And again, we need to do all 3 actions as one action to fulfill ACID criteria of transactions. So there were 2 examples, but now YDB has possibility to have to create all possible scenarios with tables and topics within one transaction. So you can read from one topic and write to the table, you can read from table and write to topic, and you can read from one topic and write to another. And previously we have, and we now have a possibility to make transactions with tables. So now all combinations of these base variants are possible, and of course several tables and several topics can participate in one transaction. Let's go further to some technical aspects. First of all, about main principles of YDB architecture. YDB has different layers for computing and storage, and the main YDB component is a tablet. Tablet is a replicated state machine which keeps its state in the distributed storage, and YDB move tablets between nodes for load balancing. And as you can see on this slide, here's more detailed picture. We have different tablets for different tasks. First of all, we have tablets for serving data entities. We have data shared tablet to serve tables. We have PQ tablet to serve topics, partition queue tablet. We had special system tablets for scheme, scheduler, and data distributed storage controller. And we have special tablets for serving transactions, coordinator tablet and mediator tablet. And I'll tell you more about it. So let's go further to lower level. The key point of distributed systems, the key point of keeping data in distributed systems is to shard data and to keep data distributed. So every table in YDB is sharded by primary key, and there are several possible methods of partitioning. So every table is partitioned by primary key. As you can see on this slide, we have here two tables, and table 1 has 3 shards. Every shard is served by its own data shard tablet. And table 2 has 2 shards, and every shard is served by its own data shard tablet. And the same idea is for topics. Every topic is a named group of messages, and it's ordered within partition. Every topic is divided into the partitions. One partition is a log of messages, so it's ordered by offset. Sequence number of the current message is in partition is offset. So offset is a property of the pair partition and reader. Several readers can read from one topic, several writers can write into the one topic. And we need partitions for scalability to increase potential write speed to this topic. Every partition is served by its own PQ tablet. And let's go further to transactions, how we create transactions with topics and tables. Key point about transactions in YDB is they have a serializable level of isolation by default. We have also less strict level for tables, but only serializable level now is available for topics. And YDB gets YQL transactions from the user. As I mentioned, YQL is our rich SQL dialect. And inside YDB, transactions can be distributed if applied to several data shards or topic partitions. And distributed transactions are processed with Kelvin protocol plus some additional thing. Here you can see distributed transaction example. We want to read a message from topic 1 and use this value as a key and update value in table 1 by this key. So if this transaction succeeds, third row will have 101 in the data field. So here you see timeline of user actions. So user begin transactions, user reads from topic 1, user reads from table 1, user writes to table 1, and then user is trying to commit transactions. And I'll tell you what YDB should do on every stage to serve this transaction. How to execute distributed transaction. YDB uses Kelvin protocol, and Kelvin protocol allows to execute deterministic transactions without locks and conflicts. What does deterministic transaction mean? Deterministic transaction is a transaction who knows keys for reading and writing. What do you think? Is this deterministic transactions or not? Okay, this is not deterministic transaction because it doesn't know the key for updating table 1 before it reads this key from the topic 1. So it's not enough possibility to work with deterministic transactions is not enough to work with these transactions, but we start from it. So, to execute deterministic transactions, coordinator arranges incoming transactions, and if it arranges this in a row and every transaction is executing on its own step, then we'll get serializable isolation. So suppose we have these transactions. So transaction TXA, which operates data in data shards 1 and 2, data shard tablets 1 and 2. Transaction TXB, which operates data in data shard and some data in topic, pick a tablet, and third transaction TXC, which operates data on all 3 shards. If coordinator order these transactions in a row, they can be executed independently. But what should we do if transaction is not deterministic? So if we don't know all keys in the beginning of the transaction. YDB can split non-deterministic transaction into the sequence of deterministic transactions. And YDB makes logs on every step. On commit, overall transaction is committed at the end if logs were not broken. Logs are optimistics, and overall transaction is committed at the end if logs were not broken. So let's return to our example. When user reads from topic 1 within the transaction, YDB log offset of this topic. When user reads from table 1, YDB makes log, optimistic log, on specific table row in this case, or on some range in other cases. When user writes to table 1, YDB stores data somewhere in the system. And on commit, YDB should check if logs were broken or not. So if topic 1 offset log was not broken and table 1 row log wasn't broken, then we can apply changes. Set new offset for topic, update table, and return success. So these transactions would be committed. In other case, transactions would be aborted, and that's it. Here we have a scheme. This is simplified scheme, but it's not so simple. How YDB components interact during the transaction. So takes proxy, the main component, assign the global takes ID for transactions, and define read-write sets of the query of the transactions. Then takes proxy define shards which are involved into the transaction, and save query paths on shards. Every shard securely save its part of work and return as an answer to TX proxy time slot for which part of query would be kept. So it returns time slot when this shard is ready to execute this transaction. TX proxy is waiting for all answers and send all this information to the coordinator. There are several coordinators in YDB, and every coordinator knows about all shards. Coordinator analyzes all possible slots for transactions for this transaction and assign step ID for this transaction. Step ID is a global identifier of step when this transaction will be executed. And on every shard, time is passing independently. So some shard at this moment of time can execute step 1, for example, and another can execute step 2. And shards are synchronizing only when they need data from another shard. So coordinator assigns step ID for this transaction and securely save step plan. At this step, coordinator guarantees that it won't be plan any this step again or any previous steps, and send this information to the mediator. Unlike coordinator, every mediator in system knows information only about part of shards. So coordinator defines which mediator are involved and send information to appropriate mediators. Every mediator is waiting for planning specific step ID by every coordinator and group transactions by shards and send information to shards. Send step plans to shards. Shards can execute this, and every shard can execute this step plan by with its own time, with its own real time. So, but every shard executes transactions in order of step ID, TX ID. So earlier step ID first and earlier TX ID first. If this shard is included in read set, it can read data, and that's all part of its work. If some shard is included in write set, sometimes on specific step, it should wait for reading shards. And when this step is over, TX proxy and one more component which doesn't exist there, KQP, it operates with logs. So KQP orchestrates logs on tables and data shard, on data shard tablets and procure tablets. So this was the general picture, and let's see what's going on specific tablets. For example, this is more simple picture. If we need to move offset, to read something from topic, we need to get data, and we need to move offset on commit. Getting data from topic doesn't require transactions because data in topic is immutable. When you read something from topic, previous information doesn't disappear. It lives until TTL ends. So, but we should moving offset by some rule. We should check the predicate that every offset is moved only in one transaction. So if two transactions are reading the same data, one specific partition, then one of these transactions would be committed and another would be aborted. For example, if we have some topic and current offset for current reader is now equals to 3, and we begin two transactions, TX1 and TX2. We read messages from 3rd to 5th in transaction TX1. Then we read messages from 3rd to 10th in transactions TX2. And then we are trying to commit tx2 first. It succeeds, and offset is now equals to 11. And we are trying to commit tx1, and it would be aborted because offset was changed in previous transaction. Offset for this specific topic, this specific partition, and this specific reader. During writing in transaction, I think it's much easier that written data is available for reading only after transaction commit. So if we have some partition with messages ABC, and we begin two transactions, tx1 and tx2. We write messages DEF in tx1, we write messages GHI in tx2, and then we commit tx2. It succeeds. Partition has messages ABC, GHI. Then we commit tx1, it succeeds. Partition has messages ABC, GHI, DEF. So if somebody reads this topic between tx2 and tx1, he or she would see ABC, GHH. That's, I think, the full picture of transactions, but we have much more details, but we haven't got enough time to cover them, but we have some important thing. So we added transactions with topics and tables, and now users can use it and can use it to serve the business logic, and don't think about atomicity and consistency of their changes. But what's the price? Of course, everything has its own price. So we've done series of tests of performance when we write into the topic within transaction and without transaction. And here you can see some examples. So test A, in both tests, we have 100 partitions, 100 writers, and 100 megabytes per second write speed overall. And difference is in test A, we are trying to write small messages of 10,000 bytes, and in test B, we are trying to write big messages. And as you can see, in case of small messages, we didn't increase write time very much, and in case of big messages, write time increases, and it could be a problem. And now we are working on some performance improvement with big messages. But you can use transactions with small messages at this moment without any problems with performance. So I go to conclusions. Now YDB can operate topics and tables within a single transactions. It simplifies user code. User doesn't need to think about atomicity or consistency of his or her changes, and it has minimal impact on latency in case of writing small messages. And main conclusion, we add ACID guarantees to topic table operations. That's it. If you have here, you have links to our community chat, documentation, and YDB repository. And if you have any questions, don't hesitate to ask.
Well, Elena, thank you very much for this insightful talk. Are there any open questions from the audience? None, okay. Then we end the talk very well in time. Thanks for your time. Thanks again. And we meet up in here back again at 11 a.m. for the next talk.